Now that we've covered the tabular method for advanced integration by parts or repeated integration by parts, let's go through a couple of problems where perhaps we could use the tabular method, or it may actually be better off for us not to use the tabular method. So let's take a look at something like number 4, for example. So if we pay attention here, we see that number 4 gives us a function that we want to integrate where both factors, e to the x and sine of x, are both transcendental. Neither are polynomial functions. So right away, I know that if I do the tabular method, I'm going to run into a bit of an issue. But just for the sake of time, let's go ahead and set this up. So we're going to set up the table in just a second. We're going to set up a table where we have e to the x sine x. So we'll just go ahead and do this. We have u slash du will be this middle column here, and dv slash d. So u will be e to the x, and dv would be sine x. So again, I'm highlighting this as my u and this as my dv. And we notice that as I go along, the derivative of e to the x is just e to the x. The integral of sine of x is negative cosine of x. The derivative of e to the x is, again, e to the x, and the integral is going to be negative sine x. And you probably can see where this is going. We are going to end up in an infinite loop here because the derivative will never get down to anything other than e to the x, and the integral will always be either some positive or negative form of either sine or cosine. That is to say that if we were to write this out, if we were to actually write this out, and perhaps we can actually see this, let me go ahead and start writing this out. We would see, okay, so the integral of e to the x sine x dx, what we're trying to find, is so far e to the x times negative cosine x. There's our UV or ultraviolet. And let me change colors here. We've got e to the x times negative sine x. So I should note that is negative. So minus e to the x times negative sine x, right? And we're going to see that this is going to continue to repeat itself here. And what I want to actually highlight quite literally here is this row right over here. Because what I want you to see here is that the integral of this, the product of this row, the integral of the product of this row is exactly what it is that we were trying to integrate to begin with. That is to say, let me just write this here, just so we can all see that. Just kind of what's highlighted here. This is e to the x times negative sine x dx. And if I actually just move that negative to the outside, then this is just here. And just compare these two. So this row, if I look at this row here to continue on, the product of this row is exactly the original integral that we were trying to find. So we can see how we're going to be stuck in a loop. I'm going to do advanced integration, or I'm going to do integration by parts again for this. And I'm going to keep on getting the same terms over and over. I'm going to keep on getting those. So how do we work around this? How do we break out of this loop? Well, the answer is just algebra. Pay close attention to what I've written out here. Notice that the integral that we were trying to find is e to the x times negative cosine x minus e to the x times negative sine x minus the same integral that it is that we were trying to find. So what about when I just add that same integral, or add that integral to both sides? Well, you can see where this is going. If I add that integral to both sides, this is going to be 2 times the integral of e to the x sine x. And now that it's gone from that side, I can say this is now e to the x. Or let me actually just make this negative e to the x cosine x. Actually, I don't even need those parentheses there. You can just write that. Plus e to the x times sine x. And how do we get rid of that 2, or that constant of 2? Which is really just me asking, so what is the integral of e to the x times sine x? If I just divide everything by 2, I just get negative e to the x cosine x plus e to the x sine x, all of this over 2. And there it is. So that's kind of a nifty little algebraic tool there to see what would happen. And honestly, had we just not approached this problem using the tabular method, you could see that a little bit more clearly algebraically. But I do want to highlight that if we were to use that tabular method in this repeated integration by parts, you know when to stop. One way to know when to stop is when the product of your row can be integrated. Product of row can be integrated. Okay, so when the product of your row can actually be integrated, then you stop and just simply integrate that row. Okay, all right, so let me actually make this a little smaller so I have some space to work with here. All right, I'll leave that over here on the side. Okay, but let's try number 5 now as another example. So again, I wouldn't use the tabular method here, but if you wanted to, just to kind of highlight this, if you wanted to, you could see the following. U and dv, at first glance, you might think, oh, x is technically a polynomial function, so it would make a lot of sense to have that be our u here. Unfortunately for us, even though the derivative of x, the higher order derivatives of x eventually get to 0, you see that that means dv would be arcsecant, and integrating that is pretty unwieldy. So instead, I am going to have u be my arcsecant of x, because I know that derivative pretty easily. That's just 1 over the absolute value of x times root x squared minus 1. dv, on the other hand, is going to be then x, and that's easy to integrate. That's x squared over 2. Now, why am I stopping here so far? Well, I could keep on integrating. However, trying to find the derivative of that gets pretty unwieldy. On top of that, if we go back to what I discussed in the previous step, or in the previous problem, about looking at the product of the row as a place to stop, right? That is, if I highlight this row here, look at this row here, is that something that we could integrate? And take a moment right now to see if you can pause the video and simplify that product and see if that's something that you can integrate. And the answer is, yeah, we can. So let's take a look at what we have so far. We have arcsecant of x times x squared over 2. That's my ultraviolet. So arcsecant of x times x squared over 2. Right? I have that. Minus. I'm doing minus here because I've got the formula for ultraviolet voodoo. On top of that, I've got this here. So minus, or I can say, if it helps at all, plus negative x squared, let me do this here. Negative x squared over 2 times 1 over the absolute value of x times root x squared minus 1 dx. And this is exactly what I have highlighted up there. Okay, let me actually just do that. That's exactly what I've highlighted up there. And I've actually moved that negative to the outside. I can rewrite this as x squared over 2 arcsecant of x minus, and I'm also going to move this constant of 1/2 to the outside, so minus 1/2, the integral of, and divide this absolute value of x into this here. So we've got x over root x squared minus 1. And we don't need integration by parts to do this. We can actually rewrite this using either the reverse chain rule or u sub, depending on how you want to think about it. So we have x squared over 2, arcsecant of x. And let's see, the derivative of this would be 2x. So I can write this as minus 1/2 integral of x squared minus 1 to the negative 1/2 times negative 2. I'm going to need a, or actually not negative 2, just 2 x dx. And now that I have that derivative of x squared minus 1 in there, I can just integrate x squared minus 1 to the 1/2. So that all becomes arcsecant of x squared over 2 arcsecant of x minus 1/4. This is x squared minus 2 to the 1/2 divided by 1/2, or times 2. That's the same thing. And there's my integral. Okay. So this problem is great for highlighting that when the product of the row can actually be integrated, product of any row in the tabular method can be integrated, then that is a place to stop and just integrate that row. And that typically will give us the final integral there.